Hi, let's do a few examples of Kirchhoff's current law, also known as KCL. In example A, you can see that we have three currents at a particular node, and what we need to do is we need to calculate what is the sum of the currents entering the node, and that will necessarily be equal to the sum of the currents leaving the node. And so then our job really reduces down to figuring out which currents are entering and which currents are leaving. You can see here that current I is entering the node, so therefore the left-hand side of the equation is just going to be equal to I. And then there are two currents that are leaving the node. Both of those are known quantities, which makes it pretty easy on us here, because as it turns out then I is just 5 plus 3, which is going to be 8 amps. Most KCL examples are not going to be as simple as that one, but that one turned out to be pretty easy. If we look at example B here, you can see that we have three currents and they're all three entering the node. And so you might think, well, that's not really possible, is it? Aren't those currents going to sort of pile up charge at that node? Well, if they were all actually entering the node, that would be the case. Clearly, that can't be true. And so before we even do any work, I can tell you that the arrow on I has to be backwards. There's no other way about it. I is definitely going to end up being a negative value. But let's find out how that works. So I'm going to have the sum of the currents entering the node is equal to the sum of the currents that's leaving the node. And in this case, the sum of the currents entering the node is all three of the currents. So I have I plus 5 amps plus 3 amps, and it's equal to the sum of the currents leaving the node, but there are no currents leaving the node, therefore this is just equal to 0. And if I solve that equation, I end up with the fact that I is equal to negative 8 amps. And as we saw last time, a negative number just indicates that the arrow was drawn incorrectly or the voltage polarity was shown incorrectly. You can imagine if I is equal to negative 8 amps, what that really means is that there are actually 8 amps flowing in the opposite direction. And so if we see 8 amps flowing in the opposite direction, that makes good sense. There's 5 plus 3 amps flowing into the node. There's 8 amps flowing out of the node. That's good intuition. But what we were asked to find is I. And I, in this case, is negative 8 amps because the arrow is drawn in the wrong direction. Let's look at example C. Example C is the sum of the currents entering is equal to the sum of the currents leaving. And you can see that there are two currents entering the node, this one and this one. So therefore, I plus 3 amps is equal to 5 amps. And we can just simply go ahead and solve that for I is equal to 2 amps. And because it's positive, that tells us that the arrow was drawn in the correct direction in the original circuit diagram. For the last example in this one, we have sum of the currents in is equal to sum of the currents out. We have two currents entering, and so therefore we're going to have I plus 5 amps is equal to 3 amps, and therefore I is equal to negative 2 amps, which just means the I was drawn backwards. So in reality, there are 2 amps flowing this direction, but because I was drawn for us and we were asked to find I is equal to negative 2 amps. So I hope at this point that you're sort of becoming more comfortable with having currents and voltages that can turn out to be negative. And if they do turn out to be negative, just remember that it just means that they were drawn backwards. Thanks for your attention.